Thanks a lot for the invitation to speak here. I'm almost the last speaker here, but nevertheless, I want to show you some topic we've been working on for a while, and I think it might be quite exciting to hear about that. I'm a professor at the University of Amsterdam, so I'm coming from the academic side, and but still, I kind of want to give you a high-level walkthrough of what position-based quantum cryptography is. So in 1969, man has first set foot on the moon, as you can see on this picture. That has been sent around the world by NASA. But in fact, there's people who don't believe that. There's people who think that this is just a hoax and it has actually been filmed somewhere in a Hollywood studio. So one could wonder, can you actually prove that you are at a specific location? And this is what we call position-based cryptography. So normally when we do cryptography, players have some credentials, something that distinguishes you from somebody else. So you might hold secret information like a password or a secret key, or some authenticated information, maybe a passport, somehow that has been issued by an authority. You might have biometric features like fingerprints or iris scans, etc. But the question I want to ask here, can just be the geographical location of a player be used as such a cryptographic credential? Can we build cryptography based on the fact that we are at a certain place? And if you, well, this might sound a bit weird, but in fact, if you think about like, well, there used to be a time when you could actually walk into a counter of a bank, and you would trust the person who is behind that counter with all your financial details. Basically, you don't know that person, but somehow just by the fact that they're standing behind that counter, yeah, there's some trust in this person. Of course, the bank has made sure only trustworthy people are there, etc. But so that's kind of a little example, and one can try to think of more examples. Of course, you can try to verify that you're actually on the moon, or you can, maybe in a more military context, make sure that a command to launch a missile actually comes from a particular place. Like your military headquarters. Or on the other hand, you would like to talk to specific places. You want to make sure that messages can only be read at your embassy in the middle of some enemy territory. Well, that's the next example. Or another example is this kind of pizza delivery problem, or trying to avoid fake calls to emergency services. So you should only be used to only be allowed to use a printer, say in this building, if you are in this building, and not like from the other side of the world, or only be able to order a pizza if you're kind of in the neighborhood. And of course, I think you guys can think of many more examples where you can actually use the would be nice to have this thing. So now, as theorists, we try to build this thing, and we start with a basic task, which we call position verification, and we make a lot of simplification. So first of all, we will only work in one dimension. So let's say all the players live on this line. Of course, not very realistic, and we can generalize. But say there are two verifiers, and there's a prover in the middle at this blue line. And the prover wants to convince these verifiers that somebody is at this blue line. And we want to make sure that no coalition of fake provers, and fake provers are players that are not at this blue line, like this evil Alice and this evil Bob. So even if they collaborate, they shouldn't be able to convince the verifiers that they are at this blue line. So that's the goal of the task of position verification. And we make, as I said, assumptions. We're going to use somehow that communication happens at the speed of light. I think that's not that unrealistic. But we also assume that computation doesn't take any time, which of course is not true. And we assume that the verifiers can coordinate. So that's just to simplify our life. And with these assumptions, let's try to build a protocol. And let's say time goes downwards, and we simply send some random string x, so classical bit string x, to the prover, and we ask the prover to return this x back to the verifier. The verifier kind of measures the time, how long it took to get the message back, and this already bounds the distance. So it's called a technique called distance bounding. So it upper bounds the distance between the verifier and the prover, because if the prover was further away, it would take this random message x longer to get to the prover and to be back at the verifier. So you could think like if you do the same thing from the other side, just send another random message y from this verifier and also measure and make sure it is the original message, then you kind of are sure that somebody has to be at this blue line. Well, it turns out that's actually very easy to cheat. If you know this protocol as evil Alice and evil Bob, what you can do simply is take this x, wait for the right amount of time, and just simply send back x. And you can do the same thing on Bob's side. Just take the y that you see here and kind of send that back in time. And to the verifiers, it would look exactly as if somebody was at the blue line. So this doesn't work. Maybe something more clever you could do is try to evaluate a function on these inputs x and y. For instance, check if they're equal or something like that. Let's call the output a and b, and then return a and b to the verifier, who would again check that these are the right outputs and also that they've been received in time. However, it's not that hard to see that also this protocol can be broken rather easily. So what Alice can do, and I'm sure you could figure this out if you had a bit of time. Unfortunately, we don't. But if Alice takes a copy of her classical string x and just keeps one for herself, but also forwards another copy to Bob, and Bobby does the same, well, it turns out at this moment in time, they both have x and y. So they can simply compute the function that the original prover was supposed to compute themselves, and then return a and b. And again, it looks as if they were at the right place. And this turns out to be a generic problem. Sorry for, down here it says position verification. I guess you have more screens up there. It says that it's classically impossible. In fact, one can prove by this argument that attackers can always play this game. So in this setting, you can actually not have protocols that are secure. However, if you paid attention, in this attack, the way they attack, there's a moment here where they actually have to copy x and y. And obviously, we're doing quantum stuff today. So turns out that quantumly, you cannot just simply copy quantum information. And so there's this no cloning theorem. So that means if you take one of these 4 BB84 states, so say this question mark is a random qubit, then no quantum operation will allow to clone this state. So this is Dolly, the sheep that we know how to clone. But quantum mechanics does not allow us to do that. So of an unknown quantum state, you cannot simply make a copy. And it's actually a pretty easy proof. This kind of first year of quantum stuff, you can write down and prove why this is at least perfectly not possible. Okay, so let's, obviously we have to make a quantum try, and people have tried this a long time ago. So let's say we send a qubit from this side, the verifier. From the other side, we send a classical bit, and this bit just determines where the qubit has to go. So it's kind of a routing protocol. If B is 0, the honest prover is supposed to kind of put the mirror here, for instance, and just send back this qubit to the side. But if the bit is 1, then nothing, it should do nothing, and the qubit just fly on to the other side. So that's a suggestion for a protocol. And if you try to break this now, then we'll see. So this side is easy because Bob has a classical bit, so he could still copy it. He could keep a copy for himself and send the bit along. But Alice here is in trouble. Because of no cloning, she cannot make a perfect copy of this unknown qubit here. And she actually, at this point, doesn't know whether she should keep it for herself or send it along. That's Bob that knows. But somehow, if she waits, then she will be too late. So the qubit, there's some probability that the qubit doesn't end up at the right place. And so we thought, well, some people have thought this actually proves that a quantum protocol is secure. Turns out that they were wrong. Because in a quantum world, you can do other stuff. You can have EPR pairs. You can have entanglement. And I think I don't really have a lot of time. So I will be very quick on this. EPR pairs. Who has not seen EPR pairs here? Where are the blockchain people? Even they have seen EPR pairs. So here's just my artistic impression of it. They are these kind of magic pairs now that haven't decided yet which qubit they want to be. But if you measure one of them, you will get a random outcome and you will collapse the state on that side. But magically, by EPR magic, you will collapse it also on the other side. And this was very puzzling to the people who discovered this. So that if you do the same measurement on the other side, you will actually get for certain the same outcome. Let me go a bit quick here. And with this, you can teleport. So you can do not the Star Trek version of teleportation, but like the ones invented by this guy. So if you have an EPR pair and an unknown qubit, you can actually teleport that qubit over to Bob. You do a Bell measurement on this side. So don't worry if you don't know the details. But the outcome of it will be a classical, well, actually 2 bits. We call it sigma. And then magically, if you do this measurement, this qubit will appear on this side. However, it's not going to appear appear in the clear, it's somewhat locked. It's actually encrypted, actually perfectly encrypted. And you need to transfer this classical key sigma over to Bob, so that Bob can unlock that key and then actually can recover this original qubit. So this is the way how quantum teleportation works. It also doesn't contradict relativity theory, but again, I'm going to be a bit fast. So once you know that you can teleport, I will show you now how you can actually still break this position verification protocol if you have entanglement. So say if Alice and Bob, the cheaters, come prepared with just 2 EPR pairs, what they can do is the following. So they're going to use quantum teleportation in the following way. So Alice has this qubit, and she doesn't know whether she should keep it for herself or send it to Bob. She's not in time. But as soon as she gets it, she teleports it over to Bob using their first EPR pair. So what's going to happen is it's going to appear here on this side. And Bob, he knows whether he has to whether Alice has to keep the qubit or not. That namely depends on B. So he will immediately also do a teleportation depending on B equals 0 or 1. And by this, so say if B was 0, he will actually teleport this qubit back to Alice. And she will have it again. She doesn't know yet. She first needs to learn B. But in fact, the qubit is back there. And so, well, and there's some more kind of things details you have to arrange properly. You have to exchange the measurement of these outcomes, etc. But somehow, it turns out they can still break this protocol. And so the question we were kind of puzzled with, well, are there protocols? Well, first of all, we could actually show that, in fact, this general impossibility also holds in a quantum setting. So if the attackers come with enough entanglement, with a lot of entanglement, exponentially many EPR pairs, then they can break any type of this protocol. So that's kind of bad news. But the fact that they need so many resources suggests the question, well, can you actually find protocols that are practically secure? So in the sense that honest proofers and verifiers are efficient, so they can just work with, Mark's hardware. But the attack requires an exponential amount of entanglement. We'll be quite happy with that. But in fact, we don't know. It turns out to be very hard to prove. There are suggestions. And this has kind of started off a long line of research. And I want to mention, because I have to wrap up, my colleague here, Florian Speelman. He's also at the University of Amsterdam. And there's already a whole line of PhDs who have worked on this topic. René, Philippe, actually Philippe's name I just saw on the door opposite this room. And more people to come. And so if you're interested in this type of work, I suggest you scan this QR code. It will be on the next slides as well. Because that is kind of the most recent overview of articles that have appeared in this line of work. And it has opened up a lot of stuff. Even, so this is just from the theory side. It turns out to have a lot of connections with complexity theory, with, it has been posed as a puzzle. There's been like world records in coming up with garden hose complexities. There's a lot of experimental problems, and people are now we're reaching the point where people are trying to implement this protocol to see, like, can we really do this just in principle? But then you run into problems with losses and measurement errors. So I've just focused on the perfect case where kinds of things are simple, but it becomes very tricky when you want to do this in practice. It also has allowed us kind of these techniques to build more advanced cryptographic schemes. There's connections with quantum gravity, with mathematics, with all kinds of theoretical stuff. So it's been a fun journey kind of to pursue this type of research. And yeah, this brings me to the end. Thanks a lot for your attention, and if you have any questions, I'm happy to answer them.
Thank you, Christian. So I lost track of time, but let's take 1 or 2 questions.
Just a quick question. So does this kind of attack model, can it be used also in device-independent cryptography settings? Like sometimes the assumption is at some point Alice and Bob cannot communicate. So I guess this violates this assumption. But suppose that I ship the devices to Alice and Bob, I'm the maker, and I have a number of like entangled qubits on the 2 devices that I do not disclose, and they are magic and last forever. Can I use this kind of resource to pull out an attack similar to what happens here?
I think there's definitely some close relation, because indeed we also study the setting where they are entangled, and when they have enough entanglement, we know they can actually do this break. But of course, the interesting setting is where they are limited in amount of entanglement, and I think then the device independent stuff becomes more difficult. So, but it's exactly on this kind of front where we are interested in these results. Yes.
Thank you.
Yeah. See one more question there.
What is known about the two players version of proving your position? So let's say you have two players, maybe they have each their own public key or something, and I'm asking classically and quantumly, and they want to prove to verifier that they are at the same place, regardless of what the place is. Is that impossible as well?
So you have two players that are at the same place, or at specific different
they
places?
pretend to be, and they have, and so can they actually be convincing while they are not, or is it?
Well, in this model, so if you are at the same place, then you're kind of the same player, because then you're kind of next to each other, and you can obviously just talk.
No, because they can, for example, have controls of two different secrets, via public key encryption, so they can actually still be two different players.
Yeah, so I think it's known that if you have like pre-shared keys, say between the verifiers and the prover, then you can run kind of like quantum key distribution protocols, and you're home free basically. So the idea is here to only use the geographical location as a credential. So in the setting of two players, I'm not quite sure. I haven't looked at it, but it's kind of a rather mean kind of a pessimistic scenario. So we give a lot of power to the attacker. They can set up anywhere not at the claimed position. So you can also think of, say, more realistic settings where there's only one adversary and he has to choose where he has to be, or he can even move around. Stuff like that has also been investigated, and then it's easier. Then there's more possibilities to have protocols which are maybe still realistically secure in practice. So there's lots of different scenarios to consider.
One last question. How does this intersect with GPS? GPS-based technologies, because this is how we use like location stuff.
I think in our model we would call GPS cheating. So we basically just want to rely on the fact that they talk to each other at the speed of light, and we kind of want to infer stuff from that. So if you have additional resources, and of course realistically you do, so then I think there's other possibilities you can do. For instance, if there's an authenticated way to communicate GPS data, well then I think it will become much easier to actually achieve this.
Thank you.
Thank you. Thanks, Chris.
Sure.